Chapter 2.2, Quadratic Functions. So in this unit, we'll be looking at first quadratics followed by other types of polynomials and finishing off with rational functions. We'll look at how to graph these functions, how to find various properties about them, etc. We're going to start off with recognizing the characteristics of a parabola, which is the shape that a quadratic function makes. We'll look at how to graph parabolas and then how to find their minimums and maximums and apply those to various problems. So to begin, the characteristics of a parabola. The vertex is the lowest point on a parabola that opens up or the highest point on a parabola that opens down. So in this picture, we have a parabola that is opening upward. We can say that it's opening upward because the arrows on either end go up. So this is opening up, whereas if the parabola were facing this direction, it would be opening down. So this is opening down, and this is opening up. So if we have a parabola opening up, then the vertex is this lowest point at the very bottom. Whereas if we're opening down, then the vertex is that highest point right in the middle. Then the graph is symmetric across a vertical line called the axis of symmetry, centered at that vertex. So if we look at this graph, if I were to fold it in half across this orange dashed line, we would see that it's exactly symmetrical. It's the same on either side. So this is called an axis of symmetry because of that. And so we can use this to help us identify various points on the graph. Specifically, the zeros. So the zeros, also known as roots or x-intercepts, sometimes even called solutions, are the x values at which y equals 0. So i.e. where the graph crosses the x-axis. So all of these words are pretty much synonymous for us. So if I say zeros or roots or x-intercepts, they all mean the same thing. So in this case, we have two x-intercepts. We can have at most two for a parabola, but you can also have one if our graph just sort of touches the axis and goes off of it. So that's one x-intercept, which happens to be the vertex itself. Or you can have none if we had something like this, where it is below or above the axis. And that's the only options for what we can have with a parabola. Then finally, the y-intercept, which I'm sure most of you are familiar with from our linear graphs, is the point where the graph crosses the y-axis, where x equals 0. So here, we can only ever have one y-intercept. That's true for any given function, and we can find it by plugging in x equals 0 is usually how you find it if you're given an equation, or we can just look on the graph as we are here. So make sure you familiarize yourself with these facts. Notice that our vertex is stated as a point, an x and a y value together as a coordinate pair. So don't state it as just the x value or just the y value. The vertex is the whole point. Whereas the axis of symmetry is stated as an axis or a line. The line, the vertical line, x equals 1, is the axis of symmetry. If you tell me that the axis of symmetry is 1, you will be marked wrong. You have to say it's x equal to 1 because that is the equation of a line. Then for the zeros, I actually have options here. I can state them how I did for the y-intercept, 0, -3, or I could state them as x equals this value. So it's really, there's options depending on how the question is asked, and I'll usually interpret what you mean by it, but our zeros are at x equals -1 and 3, or we can say our y-intercept is the point 0, -3. So however you want to state that is okay. But the axis of symmetry and the vertex have to be stated as they are. Alright, so graphs versus their functions. In this class, we will talk about 3 different ways to present a quadratic function: general form, vertex form, and factored form. So factored form you're probably pretty familiar with. It's when we factor our function. But some terms that you may or may not know. General form is the one where we just look at ax squared plus bx plus c. So this is where we haven't really done anything to the function. It's all multiplied out. It's in its simplest form, and some people would say. Sometimes Essentially, in your book, they don't really have a name for this form, so I'm referring to it as general form because some books call it that. Most mathematicians, this is where things get a little confusing, will refer to this as standard form. When you go to calculus, your calc book will probably call this standard form. However, according to your textbook, standard form is the same thing as vertex form, which we're going to learn next. So things get a little bit confusing, so if you hear the term standard form, which you will generally not hear it from me because it's confusing, but if you hear the term standard form, it could mean this form, and most mathematicians will use it that way. It could also mean the next form we're going to go over. And your book, if you see in your homework, standard form means the next form. So I apologize for how confusing that is. I don't really know why pre-calculus textbooks have a different name for standard form than calculus textbooks. It's just kind of a thing about them. They all have that in common. But anyway, so we're going to refer to this one as general form, even though most people call this standard form, but we're going to call this general form. So ax squared plus bx plus c is general form. All right. Now let's figure out some properties we can get from having it in this form. First, if a is greater than 0, our parabola opens upward. If it's less than 0, our parabola opens downward. So here, yes, you're given the equation right here, but you can also figure things out without even needing the equation. I can see that this opens up, so I know that a would have had to be positive. Specifically, it is positive 1, so we can see that that works out. The zeros are at x equals negative b plus or minus square root of b squared minus 4ac over 2a. Okay, I've said that very quickly because it should sound a little bit familiar to you, hopefully. If it doesn't, this is something you're going to have to rememorize or look into because the quadratic formula is back. The quadratic formula is a way to always find the zeros of your quadratic. So when we talk about factoring, factoring works sometimes, but not always, whereas the quadratic formula will always work, so it's foolproof, which is why it's sometimes considered the better option to use. So, make sure you're aware of the quadratic formula and how to find the zeros given this general form when we don't have it factored. Then, the axis of symmetry is x equals negative b over 2a. So, given the equation, yes, we can see in this graph that the axis of symmetry is x equal to negative 2, but let's see if that goes along with what we say here. So x equals negative b, so that's negative 4 over 2 times 1, or in other words, negative 4 over 2, which is indeed negative 2. So x equals negative 2 is the axis of symmetry, and we can see that that is true. Then we can follow that up by figuring out what the vertex is. The vertex is negative b over 2a, comma, f of negative b over 2a. Or in other words, we just plug in that point. That's how we would figure out where that x value lines up on the actual graph of the equation. So when I plug in negative 2, I get negative 2 squared plus 4 times negative 2 plus 3. So that's 4 minus 8 plus 3, which is indeed, according to this point, going to be negative 2 comma negative 1. So this is accurate. So that's how we can find the vertex given the general form. And from there, we can also figure out the x-intercepts using some rules of symmetry, some plugging in of points, etc. It's not as easy to find the x-intercept, but you certainly can. Or you can attempt to always do the quadratic formula, or see if you can factor it to make things easier. So this is how, given the general form, you would find all of that information. Now, the other side is the vertex form. So this is one you might be a little bit less familiar with. Again, in your textbook, it is called standard form. This is what probably the My Math Lab will refer to it as, standard form. I will always call it vertex form because of that discrepancy with, if you take calculus, standard form is suddenly going to mean this. And so that's very annoying, and so I refuse to call it standard form. But if you see it in the My Math Lab, it is referring to this format. Alright, so vertex form, the reason it's called vertex form by most people is because it gives you information about the vertex. So ax minus h squared plus k. It looks a little bit weird, but this is an interesting form because it's all about us placing the vertex somewhere. So again, that a is the same as it was in the general form. If a is greater than 0, parabola opens up. If it's less than 0, it opens down. But now we can also say our vertex is specifically at the point hk. So vertex form gives us an easier way to find the vertex. But why is that, becomes the question. We'll get to that in a moment. But let's just look at, I already have our function in vertex form here, negative 3x plus 2 squared plus 4. So notice that this is x minus h. So in other words, this is x minus negative 2 here. So our vertex should be negative 2 comma 4, which indeed it is. So we can see that this checks out with the graph that's pictured. And our axis of symmetry is, of course, whatever the x value of the vertex is, which is, in this case, x equals h. But what is up with this form? Where does this come from? Essentially, this form demonstrates transformations done on the function y equals x squared. So when given a graph, we can use the steps from chapter 1.6 to find the vertex form of the parabola. For example, y equals x squared looks approximately like this. See? Remember your common functions we've talked about before. So there's y equals x squared. And if I wanted to shift it over 2 to the left, well, that's going to be approximately like this. Okay, so we've got it now shifted over 2 to the left. All right, so that was y equals x squared. This is now y equals 2 to the left means it's x plus 2 squared. Then, if I want to flip it over, all right, so that's going to look like this and like this approximately. So that's now y equals negative x plus 2 squared. And so we can continue doing this so that I'm going to stretch it out. So I will be multiplying the whole thing by 3, which is going to stretch it. So now we're more like this and like this. So then that's y equals negative 3x plus 2 squared. And finally, the last step is just that plus 4 shift to get it to its final form, where we are shifted upward. So we can see that all of these steps together form the vertex form of our parabola, and it's all coming from those transformations we talked about in chapter 1.6. So if you're given a graph of a parabola, one way you can get immediately to the vertex form is to think about that those transformation steps. One last note is these two forms, the vertex form and the general form, are just different ways of representing the same function. We will later talk about how to transfer between the two, but they should give you equivalent numerical information if analyzed correctly. For example, h is equal to negative b over 2a, so we can figure out what b and a are using h. And k is f of b over f of negative b over 2a as well. So all of that should be the same, and that's one way to check your work when you are transferring between the two, is to make sure that this information stayed the same. All right, so let's look at an example. We want to write the vertex form of the given parabola. So we're going to start off with our base of y equals x squared. Then we're going to look at how it's been moved. So our vertex is shifted to the left 2, and then down 3. So that gives us y equals ax plus 2 squared minus 3, right? So this is x minus negative 2, and then minus 3 on the outside because it stays the same symbol there. So once we get to there, the only thing that's left is figuring out what a is, which is usually the tricky part, but really all you have to do is plug in some point. Any point, as long as it's not the vertex. Plugging in the vertex is not going to be helpful. But any other point will get you there. So if I plug in some point, usually I'm going to pick the y-intercept if it's not the vertex, just because there's a 0 in there and so it makes things kind of nice. So if I plug in 0, -1, this point right here, then I'm going to get the following. So I plug in -1 for y and 0 for x. 0 plus 2 is 2, so this is going to be -1 equals 2 squared times a minus 3. Okay, and so that's -1 equals 4a minus 3. So positive 2 equals 4a. And so finally, when I divide by 4, I am going to get a equals 1/2. So we have a final answer of y equals 1/2 x plus 2 squared minus 3, and that is our vertex form. Now, if I wanted to get to the general form from there, all I'd really have to do is multiply it out. If I square x plus 2, so that's going to be x squared plus 4x plus 4, all times 1/2 minus 3, and then I can multiply that by 1/2 to get 1/2 x squared plus 2x plus 2 minus 3, and then simplify it to here. So all you have to do to go from vertex to general is multiply out that, is actually do the squaring. But to go from general to vertex is a little bit trickier. If you're not given the graph, or you don't feel like going through the process of making the graph, then there is still a way to get to vertex form. So if I wanted to write f of x equals 2x squared minus 6x plus 7 in vertex form, I can start by finding the vertex. So we have an equation for that. It's the -b over 2a and f of -b over 2a. So first I figure out what -b over 2a is. So remember, here's b, here's a. So b is -6, a is 2. So we're getting -6 over 2 times 2, which is going to simplify for us. So the negatives are going to cancel out to get us positive 6 over 4, which is 3/2. So I have the x value of my vertex, and then to figure out what f of 3/2 is, I'm not going to necessarily go through those steps, we just have to plug it in. So plugging in 3/2 into our function, 2 times 3/2 squared minus 6 times 3/2 plus 7 is going to get us 5/2. So now I have this vertex point. And so creating vertex form is pretty simple from there because, as I said before, the a's match. So vertex form takes this point hk and plugs it in for h and k, but then the a is the same as it was before. So we get 2 from the original general form, and then x minus 3/2 squared plus 5/2, and you're done. So that is one way to do it. You may have also learned a technique called completing the square. That also works. You're doing essentially a very similar thing. It just looks very different. But if you know how to complete the square, that is another way that you can do this as well. Either method is totally fine, or if you know another method to do it, because there are other methods, then that's fine, as long as you get to the vertex form. Now let's talk about the domain and range of any quadratic. It's always going to be real numbers for the domain, but the range is going to be based off of where my vertex is and what direction we're going in. So again, domain, always all real numbers. You're going to find that that's pretty true for any polynomial. We'll talk about that later, though. So written in general form, if a is greater than 0, in other words, we're facing this way, then the range is starting from whatever the y value of the vertex is, in other words, f of -b over 2a. So this is the y value of the vertex. Then we just go up. But on the flip side of that, if a is negative, so we are facing in the opposite direction, then we are going from the y value of the vertex and down. So we're starting here and we go down. Makes sense. So, if we are in vertex form, though, our range is still going to do the same thing, but we just have to be aware of what our y value is. Our y value is now k instead. So it's the same basic instructions depending on whether you're using f of -b over 2a or you're using k. Either way, if we're pointing upward, it's going to be from the y value of the vertex up. If we're pointing down, it's from the y value of the vertex down. then the maximum or minimum value is that y value. So in this case, if we have a point at our vertex at -2, -4, we can say our domain is all real numbers. Our range, in this case, because it is a picture of a parabola opening upward, our range goes from -4 to infinity, including -4, and then our minimum value is -4. So if you're asked to find the minimum value, it's asking for what is the lowest point we reach, but specifically, what is the lowest y value we reach? Because it's not the minimum x value. The minimum x value is -infinity. So we just say the minimum value is that y value. It's asking for the minimum output. So again, this is where we get into the difference between the input and the output of a function. When you're asked what is the minimum value that a function reaches, it's asking for the minimum output. So remember those relative mins and relative maxes, absolute mins and absolute maxes back from chapter 1. It's all talking about output, same thing here. Alright, so to sort of finish out that, we're going to look at a couple examples. So a backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. She purchased 80 feet of wire fencing to enclose 3 sides, and she will use a section of the backyard fence as the 4th side. So our goal is to find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. And then what dimension should she make her garden to maximize the enclosed area? So you're going to see a lot of max and min type questions now. So first, in any question like this, is your first step is going to be to try to draw what's going on. So in this case, it's a little bit confusing, but we're looking at a rectangular space. So I'm going to draw a rectangle. And then so that is a new garden within her fenced backyard. She purchased 80 feet of wire fencing to enclose 3 sides, and she'll use a part of the backyard fence as the other side. So it's going to look something like this. Alright, so here's a little bit better picture of it, but that's essentially what's going on. Then we're told that one of these sides, probably the length side of our length and width equation, is going to be L, and we're going to call the other side width for the moment. But our goal is to get an equation in terms of L. In other words, we only want L in our final answer. So, what do we know? We know that there are 80 feet available, 80 feet of wire. So, we can say that our length plus width to make that perimeter has to be 80 feet. That's how much fencing we have to make these 3 sides. So we have this. So in other words, 2L plus W equals 80. Our goal is now to get rid of the W that's here. We only want this in terms of L. That's what the question asks, is find a formula that only uses L. So I'm going to take this equation and I'm going to solve for W. So I get W equals 80 minus 2L. Now why do I solve for W? You'll see in a moment. So first, I represent W in terms of L. Then I'm going to look at my area equation because my goal is to maximize the area. That was the whole goal of the problem. And we're trying to find a formula for the area. I haven't even brought up the area yet, right? So what is the area equation? Well, area of a rectangle is length times width. So, length times width, well, I just figured out how width was related to length. So I can replace my W with 80 minus 2L. And then I'll just multiply it out to make it look a little bit nicer. But in factored form, it's L times 80 minus 2L. And then multiplied out in general form, it would be negative 2L squared plus 80L. There we have an equation. It only has L's left. So it fits the goal of the question. I have an equation for the area that only has L. Alright, so then I can write it as a nice equation. A of L, so it's telling me that L is my variable, is equal to negative 2L squared plus 80L. Alright, now the next question is, what dimension should make her garden should she make her garden to maximize the enclosed area? So we can see this has L squared in it, and that's as high as it gets. This is an equation of a parabola. And specifically, since it has a negative lowercase a value, that means that our parabola looks something like this. So it has a maximum point, and the output is the area. The output is A, capital A, area. So to get the maximum area, I want the maximum value, maximum y value, or A value in this case, that the equation is going to output. So I just need to figure out, where does the vertex occur? So where is the vertex of this equation? So to figure out the vertex in general form, I use my negative b over 2a. So a is negative 2, b is 80, and c happens to be 0 in this case. So to figure out my negative b over 2a, I'm going to plug in, I'm going to plug in 80, so negative b over 2a is equal to negative 80 over 2 times negative 2, or in other words, negative 80 over negative 4, which equals 20. So negative b over 2a is 20, but this gives me just the L value, the length that's going to get me to that maximum area, but not the actual maximum area it's asking for. I mean, it does ask for what dimensions, so we'll get there. But right now, length equals 20 is the dimension, but I still want to check myself and find that maximum area as well. So I've got that the length has to be 20. Then I can get my maximum value of A by plugging in 20. So when I do that, I get 800. So the maximum occurs when L equals 20, W equals 40. In other words, 20 feet, I should say, and 40 feet. You should always use your units in a question like this, and so that's a mistake on my part for not putting units. But you should always include units when you answer a word problem. If you don't include units, you will get points off. So L equals 20 feet, W equals 40 feet. And the maximum area is 800 feet squared. Alright, so a couple more things to think about when dealing with our quadratics. We've figured out how to find our maximum and minimum value, but what about how to find the x and y intercepts? Well, to find the y-intercept, this one is something we already know. We just can plug in 0. The y-intercept is found at f of 0. So it's just going to be whatever c is if we're in general form. Plugging in 0 gets us negative 2 here because those x's go away. It might look a little bit different when we're dealing with a vertex form, but that's okay. It's still just plugging in 0 is the point. But to find the x-intercept, on the other hand, if we're given general form, there's a couple ways to do that. As I said, we have the option of doing the quadratic formula. We also have the option of factoring, depending on the equation. Not every equation is nicely factorable. Every equation can be solved with the quadratic formula. Every quadratic equation can be solved with the quadratic formula. So, if we want to factor, we're going to start with setting it equal to 0, and then going through our factoring process. So if you're rusty on factoring, this is definitely something you're going to want to look into because it is going to come up a lot. We're going to talk about other factoring methods for higher degree polynomials, but when it comes to quadratic factoring, we're not going to spend a lot of time talking about how to do that. That's something that it's covered in algebra, and so it's something that you should, if you are rusty on it, you should look into it and get some practice on it. I will be posting a practice review assignment that is not to be graded or anything, just to look at. So you should do that if you don't remember your factoring rules. So when we factor this, it does factor into 3x minus 1 times x plus 2. I'm not going to go through the process of doing that. But we set each of these factors equal to 0 independently, and then solve for x. So we get these two x values. The other option is quadratic formula, which does look more complicated, but again, not everything is factorable, and not everyone's good at factoring. Whereas the quadratic formula always works on a quadratic. So we can plug in each of our values. So we have, again, negative b being 5, plus or minus square root of b squared, minus 4 times a, which is 3, times c, which is negative 2, over 2a. And then we just have to do some simplification. What's nice about the quadratic formula is it will even give you complex answers sometimes, whereas factoring, you're not going to get these complex answers ever. That's just not... I shouldn't say ever. There are some examples where you can get the complex answers from factoring, or if you're just really good with complex numbers, it can be factored that way. But generally speaking, you're not going to get the complex answers from factoring, whereas using the quadratic formula, you will. So you can always find your answers via the quadratic formula, so I really suggest memorizing it. Now, when we simplify this, we'll notice it simplifies down to negative 5 plus or minus 7 over 6, which, when we simplify it further, I will go through these steps. So negative 5 over 6 plus or minus 7 over 6. So if it's negative 5 plus 7, that's going to be positive 2 over 6, as well as negative 5 minus 7 becomes negative 12 over 6. So that's where we get the negative 2 and the 1/3 from. So our final answers are the x-intercepts are at 1/3, 0, and negative 2, 0. Using both methods, we got the same answer. So we know we did it correct because we got the same answer both times. So that's a pretty good way to check ourselves. All right, the one more graphing example. So if I have an equation in vertex form, I want to graph 2 times x plus 4 squared minus 8. So first, I'm going to take note of which direction it opens in. It opens up since a is 2, which is positive. Next, we look at the vertex. Remember, the vertex is hk, but this is negative 4 is what's going on here. So our vertex is negative 4, negative 8. And so I place a point there. Now, the fact that our parabola opens upward just sort of gives me some information that is going this way, but it's not super necessary to help us draw it. It's more a way to help us check our work at the end. Because if you plug in these numbers wrong, then you might get it facing in the wrong direction. But it's a very easy way to check that at least you're going the right direction. Now, the axis of symmetry is, of course, at the x value of the vertex, so x equals negative 4. And so, again, if you plug in numbers wrong, axis of symmetry can help check your work. So when we plug in our y-intercept, that's just plugging in 0. So 0 plus 4 is 4, squared is 16, times 2 is 32, minus 8 is 24. So we get a y-intercept at 0, 24. As well as x-intercepts at 0, negative 2, or at negative 2, 0. Oh, that's miswritten, I apologize. Negative 2, 0, and negative 6, 0. So that's from, again, setting our equation equal to 0. So we can do this, we can go through the steps of solving that, etc., or we can use some symmetry to help us there. So, and I haven't put the y-intercept on here simply because the graph would be too tall. So y-intercept is way up there. But that helps us check again that we are going in the right direction, that our y-intercept is somewhere way up here. All right, and then we just draw our actual parabola through these points, like so. And so that gives us a pretty good idea of what it looks like. So again, I apologize for that. I will fix that before I post it. But we have our graph. And so that's it for our quadratic section. So hopefully you have a good idea how to graph a quadratic as well as how to work with the two to three different ways we can look at an equation. Again, the general form is the one where it's ax squared plus bx plus c. So it's where, it's like in question number 2 here, where we really haven't done much to it. And then we have vertex form, which, again, your book will refer to as standard form. The MyLab homework will refer to as standard form. I don't call it that, but it is what you are expected to know it as in the homework. So, standard form or vertex form in this case is just the form that tells us where the vertex is, and it also demonstrates how our graph has been shifted using transformations. And then finally, factored form is the third form. And so again, if you are rusty on your factoring skills, make sure you're looking into practicing that, because it is going to come up a lot in this unit. So you have to know how to do it.